Imagine the surprise when strange islands and hidden springs began appearing in the Great Salt Lake, challenging what scientists thought they knew about this vast saline body. As the lake's water levels continue to drop, these mysterious formations offer a new window into the lake's hidden secrets. Over the past few years, researchers have noticed peculiar mounds covered in phragmites, an invasive reed, emerging on the drying playa along the southeastern shore of the Great Salt Lake. Initially puzzled, a team of geoscientists from the University of Utah has been working diligently to uncover the mystery behind these reed-choked oases. By deploying a network of piezometers and conducting aerial electromagnetic surveys, they are beginning to piece together the puzzle. Professor Bill Johnson, from the Department of Geology Geophysics, hypothesizes that these circular mounds form where a subsurface plumbing system channels fresh groundwater under pressure into the lake and its surrounding wetlands. During a recent visit to one of these mounds, known as Round Spot 9, Johnson and his graduate student, Ebenezer Adamarco Mensah, were checking on the piezometers they installed last year to monitor underground water pressures at various depths and locations around the island. Water in the lake has spent a significant amount of time underground before reaching the lake. But the exact path it takes remains a mystery, Johnson explained. Did it originate in the uplands, seep through the ground, and then emerge in streams before flowing into the lake? Or does it travel directly to the lake? To map the subsurface of the lakebed, Johnson enlisted the help of Expert Geophysics, a Canadian firm, to conduct airborne electromagnetic surveys over Farmington Bay in February 2025. Using a circular device suspended under a helicopter, the team collected data that will help locate freshwater deposits beneath the lakebed. The equipment generates an electromagnetic field that penetrates deep into the ground, and a receiver records the signals bouncing back, providing a 3D image of the subsurface. This data will give us a detailed picture of the magnetic fields beneath the Earth, allowing us to create a comprehensive 3D model of the subsurface, said Jeff Sanderson, a crew leader with Expert Geophysics. As the lake continues to shrink, the exposed lakebed becomes a significant source of wind-blown dust, affecting Utah's population centers. Johnson's research aims to determine if the groundwater can be harnessed to restore the lakebed's crusts, potentially reducing dust pollution. It appears that this groundwater could be a valuable resource in the future, but we need to understand it thoroughly to avoid overexploiting it and harming the wetlands, Johnson emphasized. He has been part of the Great Salt Lake Strike Team, a university-state agency partnership dedicated to reversing the lake's decline. With new data in hand, Johnson secured preliminary funding from the Utah Department of Natural Resources to further investigate its underground water resource. His team, which includes other senior geology faculty members like Kip Solomon, Mike Thorne, and Michael Zhdanov, is working to map the extent and depth of the freshwater beneath the lake. For instance, Solomon's lab is using isotope analysis to determine the age of the groundwater and its recharge elevation, or where it originated in the mountains. Thorne is constructing on-ground resistivity profiles, while Zhdanov and Michael Jorgensen are processing the electromagnetic data to build a 3D image of the subsurface. Our goal is to map the boundary between fresh and salt water and locate the freshwater springs discharging groundwater into the lake, Solomon said. He plans to present preliminary findings at the Geochemical Society's 2025 Goldschmidt Conference in the Czech Republic. Johnson's interest in the groundwater mystery began a few years ago when he observed something unusual while traveling the north arm of the Great Salt Lake by airboat. Water and gas were churning the surface in a circular area about twice the size of the airboat, suggesting a powerful influx of groundwater. I was curious about what was causing this, as it seemed like a significant amount of groundwater was entering the system, Johnson recalled. Later, he and his team noticed similar mounds occurring on Google Earth images of the Farmington Bay playa. Traditionally, it was believed that direct groundwater discharge accounted for only 3% of the lake's water budget. However, Recent data using chemical mass balance methods suggest it could be as high as 12%, revealing new insights. Johnson's team has discovered fresh water at depth in several spots far offshore, which was unexpected. They found fresh water even beneath the causeway in Farmington Bay, contrary to the assumption that it would only be present at the periphery of the lake. We found fresh water almost everywhere we've looked, even in tight sediments 30 feet below the surface. These sediments extend up to 10,000 feet deep, and while we're not sure if it's fresh water that deep, it's certainly fresh a long way down, Johnson noted. At round spot 9, Johnson's teams has installed 3 sets of 4 piezometers at various distances from the edge of the 250-foot diameter island. The instruments, placed at depths of 7, 11, 30, and 60 feet, are connected to the surface via white PVC pipes. Regular visits by Johnson and his students, such as Adamako Mensah, have yielded intriguing data. The near-surface water is the purest at the center of the mound and becomes more saline toward the edge, while deep water remains fresh at all locations. This suggests that the groundwater is under pressure and primarily emerges at the center of the island. The data shows that the fresh water in the center is under significant pressure, indicating a strong hydraulic head. This pressure is also present at the perimeter, but the fresh water is capped and doesn't reach the surface, Johnson explained. Johnson believes there are hundreds of these groundwater-fed oases scattered across the exposed playa of the Great Salt Lake, hinting at a vast underground reservoir. With the help of his colleagues, he hopes to trace the origin of this water, determine when it fell as snow, and estimate the total volume available. We must be cautious about characterizing this as a readily accessible water resource. It's much more delicate than that, and we need to understand it better before making any decisions, Johnson concluded. But here's where it gets controversial. Should this groundwater be considered a potential resource for mitigating dust pollution? Or should it be protected to preserve the delicate ecosystem of the Great Salt Lake? What do you think? Share your thoughts in the comments below.